Welcome to the third video in this series. The topic this time is quantum theory. In this video, we will start to build up the most important elements of quantum theory, the Schrödinger equation and the Heisenberg principle, just by defining states and operators, and then let them evolve in time. Then we will move from these abstract ideas into representations. We will also give an example of one of the systems that one can solve, that is the potential with the harmonic oscillator or the harmonic potential. And then we will upgrade the Schrödinger equation into its relativistic version or relativistic partner that is called the Klein-Gordon equation, which actually describes quantum fields and not just what quantum theory deals with. In the end, we will finish with the idea of how particles pop into existence from the vacuum and what quantum fields have to do with that. Okay, let's get started with quantum mechanics or quantum theory. So quantum mechanics is a very nice historical approach with all the experiments, and they are really cool and very interesting. However, we will completely skip all of these now. In this video, we will build out quantum mechanics from a purely theoretical approach. So indeed 3.1 is quantum theory. And so as we had the speed of light as the characteristic constant in special relativity, now we have the Planck's constant, which is denoted as h. So this is the Planck's constant is the characteristic number, and there is a version which is called the reduced Planck constant, or h bar. This has the units of joule seconds, and essentially it has a value of a number which we will now actually set to just 1. So just imagine that we rescale all of our constants. So the Planck constant is just going to be the number 1. This is going to make our life quite simpler, and because every time we just multiply with the Planck's constant, then it's just multiplying with 1, so we can get rid of it. Sometimes I will write it out so that just things are very clear that we included this thing. Okay, so as a starting point, we should discuss that there is a huge difference between classical mechanics and quantum mechanics. The state of a system is not the same as the measurement of the system in the quantum mechanical approach. Let's denote the state with the Greek letter psi. So psi is the state of the system. So you could think about as an electron being on a given orbital, or actually essentially anything else. So it's a very, very general statement that this is the state of a system. If you use Dirac's notion, then we will put this weird bracket around it. So this is actually called the cat. So cat, it's the notion from Dirac. And we will see later why this is relevant and why it's actually called cat. So that's going to come up very soon. And let's call the measurement with an operator. So I'm going to denote operators with a hat. So a hat is an operator that does a measurement. So it measures the parameter a. So in classical mechanics, the state is characterized by the result of the measurement. So we said that A measures the parameter lowercase a. So let's just say that we launch the rocket, and and then when we look at it and we see that it is a kilometer above ground, then its state is going to be that it is a kilometer above ground, and the measurement is also saying that it's a kilometer above ground. In classical mechanics, the state is essentially the same as the measurement. In classical mechanics, this is true, but in quantum mechanics, which I believe is QM, this is not true at all. In quantum mechanics, the state, the psi, lives in an abstract space called Hilbert space. So the H is for Hilbert. Hilbert was also a mathematician. So when we act on a state with the operator that measures stuff, so the A operator acts on the state psi, then it's going to give us the A measurement and the psi state itself. And as I mentioned earlier, that we could say that the state is that the electron is on the 1s2 orbital, and then this measurement can be the location of this electron. States can evolve. Evolution of state. And this evolution is described by an operator which we call U. When we evolve a state, that state is still going to be in the Hilbert space. So what this U does is that it moves an element of the Hilbert space into an element of Hilbert space as well. So essentially, when we get a new state, let's just call it psi prime, that we do by acting on the original state psi with this U operator. So this U operator is a unitary operator, and that's why it is actually called U. So U is unitary. So if you don't know what that means, there is a video about matrices and unitarities is included there as well. Essentially, just a quick reminder is that when we do the U dagger multiplied with the U, we get 1. That's what unitarity means. So this is how a state can evolve in time, but also the results of the measurement can change. So the evolution of the measurement is the other thing which we can speak about. And so this same U unitary operator is the one which gives us the evolution of the measurement. So let's just say that the A measurement will become A prime measurement, as earlier the psi became psi prime. So that's happening by taking the dagger of the U, multiplying it with the A operator, and multiplying that with the U operator. So this is how we describe the evolution of the measurement. And earlier we had the description of how the state changed. So these U's as of now were really just abstract operators, but there's a subset of these operators which will depend on a parameter. So subset of U is such that it's a U which depends on a parameter which I'm now calling B. And so these, well, there is a subset which also forms a so-called group. And I think there is another video which is describing groups in general. And this group is actually called a Lie group, and it's a continuous group. One of the main properties of this group is that for all parameters, let's say b1 and b2, there exists a b3 in a way that we do the operation for b1, and then we do the operation for b2, and we get the operation for b3. So one example that we can come up with is rotations. So I can say that that this was a rotation by 45 degrees, and this was a rotation by another 45 degrees, could be anything. Then, when I rotate an object with 45 degrees, and then I rotate the object with 45 degrees again, that's the same thing if I would rotate the object with 90 degrees in the first place. We can have a standard parametrization of these Lie groups. So standard parametrization. First abstract point of view, when we have the b parameter to be 0, then we want the operation to be the identity 1. So, going with this example again, if I rotate with 0 degrees, then it doesn't do anything. There's no change. So everything with the blue is abstract, but everything with this orange is just a very specific example with rotations. Okay, let's do the next step, which is that we do just a little change. So, if I go from B to dB in a way that that's just an infinitesimal version, that's the same as doing nothing, but then doing a little bit of of uh, of this change. So, if it was rotation by 1 degrees or 0.0001 degrees, and then it still needs to be an operator. So we include something which we call t, and also there is something which we factor out from this t, which is the complex number I. There is a video about complex numbers again, if you are interested to check that out. So this t is called the generator, generator of the of this operation. And the I and the -1, minus I, it was just a convention. Totally could be a positive number, and then the U dagger will be the negative number, so it doesn't really matter. And the mathematicians sometimes keep it just include the I in the generator. Physicists like to factor it out. So the T is the generator of the group. So what I was mentioning with this convention is that if I take the dagger, the adjoint of this operator, then I go in that direction, so it's going to be plus I t dv. By the way, I actually neglected that there could be other terms here. We could have db squared, but what we just do in physics is that we say that, oh, this is a big old notion of dB, we are neglecting them all. So that's how we just end up with this formula. So the U dagger is that I take the convex conjugate, so the -1 will move to +1, and the T will become the adjoint of the t as well. So that's a t dagger here. So unitarity had this statement that the u dagger u is the same as 1. If I multiply with the inverse of the u, right? So if I multiply this with the inverse of u, then on the left side I just get u dagger, and on the right side I get u minus 1. So that it also means that this is going to be I1 plus I t. The inverse of an operation is 1 plus I t with the hat and tb. Why is that so? Well, if again we were rotating in the original case with small 1 degree, then the inverse of rotating to the left, so here we could be saying that we rotate, with minus 1 degrees, and from that, the inverse of that is going to be rotation to the other direction. So it's going to be plus 1 degrees. So that's how I move from this to this. And as I said with this minus 1, this is totally conventional if I call the u dagger with a plus or with a minus. Okay, so we learned something from this because we now said that the inverse is that, but then the u dagger was this guy up here. So putting this in with the blue, this was the same as 1 plus I t hat dagger dB. So everything is the same here except that we have a t on the left and a t dagger to the right. So this means the t operator is the same as the t dagger operator. And so that was our definition for being a Hermitian operator. That's the same thing with what we discussed with unitarity earlier. Okay, so next thing to do is that, why don't we do these small steps n times? So if I have u dB to the power of n, so that just means multiplying u dB with u dB with u dB with u dB n times. And so if this is going to be still a group, because of what we discussed earlier from this property, that this is a lot of multiplications here with the power, and that's going to be again just a member of the group. But then we can also say that we define this the two things. Essentially we define n in a way that the b is the same as n times dB. So when we do this, this will lead to saying that this is UB. So what is the meaning of this? Well, the meaning of this is that instead of moving 1 degree, 1 degree, 1 degree, 1 degree, 1 degree, 1 degree, instead of moving 90 degrees, I will just move 1 degree all the time. So instead of 1 times 90 degree, what we do is that we do 90 times 1 degree. Right? This is just a physicist trick that we do some big change in small steps. So from this, we can say then that the dB is the same. dB is the same as the B divided with N. So, and then with the UDBN, we can just use this definition here that that was 1 minus I, the generator, dB. So then this will lead to saying that we get UB, so UB is the same as UB dB n times, and to the n factor, so n many times multiplied with each other. And then the definition of the UDB was that it is the same as 1 minus, and we had the IT operator, and then we had the dB, which is now defined to be b over n, just from here, and we take this to the nth power. So this is something that could look very familiar from the Taylor expansion studies, about which I have another video. So if n goes to infinity, then this whole thing will be the Taylor expansion of the exponential of minus I t operator and the parameter b. Okay, so this actually leads to some very important conclusions here. When we want to describe an infinitesimal change, so the inf change in the state, which was the change itself was the psi prime is the same as u t b operator times the psi state, which now we figured out that it is, well, from these things, that we figured out that this is 1 minus I t operator dB of acting on the state psi. So that leads to just multiplying in with the psi state itself minus the I, the t operator, the psi state, and the dB. And we can also speak about the infinitesimal change in the measurement. So earlier we discussed that a prime, which is an operator prime, we get by doing the u dagger, which now depends on this dB. It's just a small change, an infinitesimal change. The original a operator and u dB. So then the u dagger was described by 1 plus I t operator dB, and then we have the a operator, and we have the same thing with the minus sign, 1 minus I t dB. And so this, after we do all the multiplications, we get terms which are like a times t minus a. So we will introduce something which is called a commutator. So this is the same as a hat plus I, and the notion for the commutator is this bracket, comma, a hat, bracket closed, dB. So I introduced the intro commutator of a and let's say b now in general operators is defined that a comma b operator commutator is the same as the a operator multiplied with the b operator minus the b operator multiplied with the a operator. So again, an example is that if you rotate an object in the xy plane first, and then you rotate, out in the plane, I can't really draw that, so out of the plane, that's not the same as doing the out of the plane thing first, and then rotating inside the plane. My drawings are not useful at all, I know, because it's in 3D and I can only draw in 2 dimensions. But the point is that you really just do it with your hand, and if you rotate in one dimension or one plane and you rotate in the other plane, that's not the same as first rotating with the second plane and then rotating in the first plane. There are certain situations when these things are the same, but then that that's not the general situation. Okay, so all these things lead to the following kind of summaries, like little conclusion. Is that the change in the psi, which I'm going to call d psi, so that was just subtracting these two, is what I call d psi. So I am left with this minus it psi dv. So the change in the psi is minus I t operator, the psi, and dB. And the change in the A, again, what I do is that I subtract this and this is the same as the newly introduced commutator of the generator and the measurement operator itself. In this next section, we are going to discuss Schrödinger's equation and the Heisenberg's uncertainty principle. So 3.2 is the Schrödinger's equation plus the Heisenberg principle. So in the previous section, we discussed that when we have a change in an abstract group, that could be described with an exponential of minus I, and then we also had the generator t and the parameter b in here. So that was super abstract in general. Nothing really had to do with physics at that point. So let's just move now and introduce these parameters to be space and time. So why not just set the b to be time, and then the operator, which is that this means that all this change is happening in time. So we have the u hat t described like this. This is describing the evolution of an operator in time, and the operator which corresponds, the generator which corresponds to this is going to be the Hamiltonian operator. We discussed earlier that the Hamilton function was the kinetic energy denoted with T plus the potential energy denoted with the uppercase V. So now that if I input these things, so that was the T operator, that then we get that the description of a change in an operator is going to be described as the exponential of minus I. And so actually there is one more thing coming in, now that we are discussing physics, that this H is going to be an operator which measures the energy. So if we think about what is the unit of the H, that's joules, and then our parameter is now T, which is measured in seconds. So that's seconds, and we have an issue here. Now that we're discussing physics, we have an issue that there is some unit in the in the exponential. So what's the exponential of kilometers, right? What's the exponential of joules? What's the exponential of seconds? It's something which makes no sense. So we need to, every time we put something into the body of, of a function, we need to make sure that there are no units included. So we need something which has joule seconds as a parameter, and we discussed earlier, and that's going to be the h bar, the reduced Planck's constant, which has joule seconds as a unit. So I'm writing here out because this, now that we're discussing physics, we need to make sure that there are no units included in the function. Later, I might not include the h bar just because we set it to 1. So whenever I divide with 1, it's just going to be not doing anything. But for now, let's keep it. So then the other changes, what we described, is that when we have this state which now depends on time, so the psi state depends on time, it's going to be described by this exponential of minus I over h bar, Planck's constant, the Hamiltonian operator, then the time, and we had this thing earlier. So I'm really just using the same formula as we derived earlier, just input that now the parameter is t instead of using b earlier. So for the measurements, it's going to become this is the inverse of or the adjoint of this. So the ad minus something will become ad plus something. So this is ad I over h bar, and then we have the uppercase h for the Hamiltonian. We have the time for the parameter, and then we have a as our operator for the measurement, and then we have the u, which is again this ad minus I over h bar of the Hamiltonian multiplied with the time. So I really didn't do much. I inputted t for the parameter. So we had this equation showing that that the psi was the same as minus of the t generator, and had dB here, and we also had an I here. So this will now become that d psi is the same as minus I over h now of the Hamiltonian operator, and oh yeah, there was this psi here as well, and so the psi itself state, and we had the dt here. So as physicists, we really like to just divide with these infinitesimal parameters, and from this we get a derivative then. So the derivative d or dt of the psi is the same as minus I over h bar of the Hamiltonian acting on the psi state. And so we can actually do one more thing. Let's just multiply with h, and let's also multiply with I. So when we multiply with I times I is minus 1, so minus 1 plus multiplied with minus 1 is just going to give us a plus 1 here. So we have a plus h acting on the psi here, and we have I h bar and the derivative of the state by time here. And so this is the Schrödinger equation. So please note how little we have actually done. We were discussing how operators change in time, and we were abstractly just having parameters, which we now replaced that the parameter which we are changing in is time. So the time change of a state is just described by the Schrödinger equation, and we derive the Schrödinger equation in these very few steps. So that's something big, I would say. You can see that the Schrödinger equation is not really an individual equation as it is. It's just a direct consequence that time is making things change. There is a time evolution of the states. If there is no time evolution, if the psi doesn't change, that this whole derivative is just zero. So now that we discussed the time changes, let's describe a bit how the space changes. So about the space, let's just start doing all this thing with a one-dimensional case. So we have a 1D case, x, and then later we will generalize it to 3D. So let's just define an operator that measures the position. And as you remember, we were discussing earlier in the Lagrangian that the general coordinates were described with q. So I'm going to use q to be the operator that measures the position. So measures the position. And we should also define this other operator that shifts the position. Shift the position. So as of now, just randomly I will pick a letter. I'm going to pick the letter P. So if we shift the position with a little, which we will denote with infinitesimal, and we are in this x dimension, then shift the position with dx, let's say, then the notion will be that this little change in the q operator will measure that we shifted this thing with x. We earlier had this general statement that when we change the a operator, that's going to be minus I and the t generator and the a operator itself, right? So let's again now just plug in that now the a is going to be q, and the t, the generator of this thing, is going to be the p operator. So the dq operator is the same as I, and again we have an over h bar incoming just because of the physics units. And so we have this commutator of p and q. And we also have dx here. We have dv here. And so this thing is the same as dx, as coming from here. And essentially, this whole thing leads to the Heisenberg uncertainty principle. That is, that if I exchange P and Q, then what we get, and I multiply with I and H, I get that Q operator, which measures the position, and the P operator are not exchangeable because their commutator gives a non-zero number. So this is the Heisenberg equation or uncertainty principle. So again, please note that this is not really an individual equation. It's just a direct consequence of displacements in time. And if it was zero, then we wouldn't have the Heisenberg uncertainty principle at all. But apparently it's not zero, it's a complex number. And because of that, this principle exists. And as the next step, let's discuss representations. So 3.3 is representations. And so we will have a subsection called 3.3.1 where we are discussing something which is called a wave function. So as of now, everything which happened up there earlier was just some abstract notion. So let's now make these things something which is less abstract. So the wave function is a function, as the name says, and it's understood as the scalar product of the position vector and the state vector. So psi is now a function, psi x, which is going to be the multiplication of two vectors, x and psi. So maybe here I should make a little bit of road. So we discussed that this thing was a ket of psi. I could also write another vector, which is the covariant or contravariant version of the same thing, that is called the bra. So you could imagine that this is that, and then this is this kind of vector. So when I multiply a scalar multiply with these two things, when I multiply a bra with a ket, I will get a number out of it. So, and then, we can just get rid of this part and just denote this as x, one horizontal line psi. It's a vertical line, sorry. So that is the wave function. It's when we have the state, and then we have this vector denoting the position. These two things together are leading us to the wave function. The next thing is the position representation. 3.3.2 is for position representation. So what we want to do is that we want to measure the position of our state. The abstract equation that we had earlier was that psi prime is going to be this q operator that measures the state of the wave function. So we said that we can discuss the wave function of something by multiplying this thing with the x. So the x prime wave function with the x as a variable will look like what we had here, the q psi multiplied with the x from the left. Exactly what we did up here. Okay, so what does the q do? The q was defined to be the one that gives us the location. So q was what measured where we are. So where are we? Well, let's say that we are at the point x. So this will lead to the point x. So when we apply the q, and so we are left with the x and the psi, two vectors multiplied with each other. But then we can go back again, and say that well, the wave function was just exactly this. So this is the x times the psi wave function. As the measurement of the position is represented as a multiplication with the value of the position. This is very important. The measurement is some operator, and we represent it with where operator just means that you do something with something. So that something that we do here is that we multiply with x, the position. That's how we represent measuring the position. Measuring the position, again, I repeat, is just multiplying with the position. Moving on to something this might seem like something very trivial. So let's move on with something which is less trivial, and that's going to be the momentum representation. So earlier we said that when we had the change in the A operator, that was multiplying U dagger with A and U together, right? So A prime was operator was U dagger operator A operator times U operator, right? We said that this is how a measurement operator changes in time. And then we also discussed that when we looked at the dA, then we had this minus I, the t generator, and the A operator, and the change in the parameter dB. So the two abstract things. So then I move this down, and I get a derivative. So I could say that I want to derive this guy. So also kind of dividing with the parameter. So let's just say that again in a general way. Now I will say that B will equal A, and so I did derive by that. Let me change colors. So d of the derivative by A of the exponential of I. You remember that earlier we had put plus I here, and then there is going to be minus I later. So I, the generator, which in this case is the P operator, and we have the variable A in this case. So, and then we have the Q operator, and then we have the same thing with the minus version P A. So the result of that is that we have the I coming down because that's what's in front of the A in the exponential. So this is a chain rule what we're doing. And then we are also left with the exponential of I, P, A. And then we have the Q and the add minus I, P, A. Let's not forget that this is an operator. And we subtract from this I add I, P, A operator, Q operator, and I minus I, P, A. So because this is two functions which depend on A, so this is x times y function derived that is in this form. And so this will equal to 1. Let's now say that if this A parameter is 0, so there is no change in the location, then the add I P operator A times the Q operator times add minus I P A. Well, if A is 0, then all this is just 1. So this all will lead to the Q operator itself. So if I merge these two information together, what we learned here and what we learned here, then what we get is I add I P operator, A Q operator, add minus I P operator A is the same as the Q operator plus this A change. Maybe we should say that at this point we also used the relationship between P and Q, like that, and we could say that we got to this result. You know, if A is 0, then we got back that this is Q, so we obviously multiply with the A and also putting it here. You know, the Q minus the inverse, which is going to get to minus A. then that leads to a 0 with the a factor. Let's now speak about that we have a state at position x. So the state at x position, we will denote that with x, and we will act on this x on the operator that we are discussing now. So that was the exponential of IP operator A, the Q operator, and the I minus E had minus I P A. So this will lead to saying that this is a Q plus A based on what we learned here, acting on the X operator. Let's multiply our equation with A had minus I P A from the left. So if I multiply this part with this blue, then that's just going to give us 1. So we have a Q operator, and then we have minus I, P, A here, acting on the X state. And then this is just, I really write it in, this is the exponential I, P, A, and acting on the Q operator plus A, which is acting on the X state. So that further equals to I add I P A X, right? When the X the Q operator acts on the X, it gives us the location, which is just a multiplication of the state with X plus A. And we have the exponential minus I P A acting on the X operator, right? So, sorry, acting on the X state, not the operator. So the conclusion from all this is that A add minus I P operator A acting on the X state is the same as the state X plus A. So you know that this was denoting where we are, and that's what we got here. And discuss the other deduction that when we act on the X vector in the bra form with I P A, then we get the X plus A as a bra form. So the physics is exactly the same here. Like it doesn't really depend if we denote the state with X with a bra or a cat. It's actually again the same thing as describing a state like this or this. It's the same physical system, so it's just a mathematical representation as of now. So all this just means that we moved the state. So if we apply this to the wave function, if we get that x add I p a acting on the psi state gives us the x plus a state multiplied with the psi state, which leads to the wave function at the x plus a position. So what we can do now is that we could expand both of these terms. So Taylor expansion. Again, there is a video about Taylor expansion in my math background for physics. You should check it out if you don't know what's happening. So we do the Taylor expansion of the exponential, and we do the Taylor expansion of this function, which leads to a bunch of derivatives. And so the next thing we do is that we equal the terms which corresponds to the same a's. So equaling terms with the same a's. So that leads to, the exponential. Of course, this is called the sandwiching when we put an operator in between two vectors. So the sandwiching stays there. I have x, and then now here I have the Taylor expansion, and then continue with the psi. So it's easy to deal with the Taylor expansion of exponentials because they are going to be exponentials. And so what you are left with is just that whatever is in front of your parameter goes down. So IP is going to come down, and if you do this n times, then it comes down n times. And on the other side, we will have a derivative by x n times of the function psi x. So this is again something which I'm covering in the background video. This is when you have a function and you go a bit side of it with an a variable, then how does the Taylor expansion of that look like? So the outcome of this is that this IP operator, which is the momentum operator, is essentially the derivation operator, dx, right? Um, this is just the psi x here. So IP to the nth is going to be derivative to the nth. So IP is just going to be the derivation. And so from this, if I multiply with I, then I get minus p here, so let's multiply with minus I. So that leads to p operator, the momentum operator, to be a derivation by x, or derivation by a component. And I again included the h bar here just for dimensional purposes. And of course, if we are in more dimensions, then this was px operator. So if I really want to describe all of the dimensions, then this is going to become the nabla. There is another video about the nabla in the vector algebra part. Let's now deal with the representation of the Schrödinger equation. So 3.3.4 is the Schrödinger equation representation. So earlier in the second video, we described that the Hamilton is the sum of the kinetic energy denoted with the T plus the potential energy. And we also discussed that the T can be calculated as P over 2m, P squared over 2m. So then that leads that the Hamilton operator is described by the P operator squared over 2m plus the V potential at the x point. However, the x becomes x with a hat, so it becomes an operator. If you remember, as we just discussed, that the x operator multiplies with the x, while the p operator does a derivation. We also described in the Schrödinger equation that the representation of the energy, essentially the Hamiltonian, is done by a time derivative. So the h, the operator for measuring energy, comes from the fact that time changes. So that was the ih, the derivation by time. And we also discussed that the p was the ih and derivation by all the space, which was denoted with the nabla. So let's just plug these things in here and get that, well, okay, maybe I should say that x was multiplying with x. So let's just plug all these in and say that I have h, which was this I h bar derivation by t, and I have applied that to the psi state. That equals to the square of this thing. So the square of I is going to be a minus sign. The square of h bar is h bar squared. The square of nabla is, I could just go with the nabla squared. And then I have 2m, which is for the mass, down here. And then I have the potential x operator here acting on the psi. And in one of the marks videos again, we discussed that this nabla squared is denoted as a triangle, which is called a Laplacian operator. So then that leads to saying that it's another form, same meaning, is that minus h bar squared over 2m, and then having the Laplacian operator plus the v potential with the x operator acting on the psi state is the same as the I h bar and then the time derivative of the psi. So now finally we have, and again it is a reminder that this thing was just the h bar. Now we have a representation of the Hamiltonian, and we see that this is the time-dependent Schrödinger equation in one form. So this is a second-order inhomogeneous partial differential equation, which essentially gives the answer to every question in the universe. Although we know that the answer to all the questions in the universe is 42, but as of now, let's just say that when we have a state and it's changing, then this equation will tell you how it will look in the future. Well, the only problem with this is that we can only solve this equation for some general cases, and it's also not relativistic at all. So there was no relativity included here. There is no c, right? With all the relativity, we need the speed of light included, and so that's not here. So this is not a relativistic equation, and we have issues with solving it analytically at least. Let me also do another representation so that you see that all the abstract stuff earlier was really just abstract, and when we are discussing how to calculate stuff, that could be done in different ways. So 3.3.5 is going to be another representation, another rep of Schrödinger equation. So let's just handle the problem in the general case. Let's just solve it for the specific case of that kind of works for everything around. And so, because earlier in the equation there was just a general thing for the potential, so we need to figure out some potential to really describe this equation fully. And so what we are going to do is called the harmonic potential. So the harmonic potential. So that's the same thing as the harmonic oscillator, like the equations that describe the harmonic oscillator, which can be imagined as an object on a string with a mass. But it's a funny thing to say that I think it was Sidney Coleman, one of the big developers of quantum field theory, who said that the job or something like that, maybe not the job, but like maybe the career path of a young theoretical physicist is to handle the harmonic oscillator in a more and more abstract way. And that's actually kind of true. So now we are going to use this formalism for quantum field theory. So we said that the V potential is 1/2 times m, which is the mass, the omega, which is omega squared, actually, which is the frequency of the oscillation, and we have the x, which is an operator we should not forget, squared. So this is the harmonic potential. So now if we plug this back to our Schrödinger equation or the Hamiltonian, we get that H as an operator is the same as p squared operator 2m plus 1/2 m omega squared x squared, where x is an operator 2. This has the form of a squared minus plus b squared, right? If it was a squared minus b squared, then we would have this identity that a plus b multiplied with a minus b leads to this. So now that we need to change somehow that we multiply these two things together, we get a negative times of the negative. So somehow what we need is when we multiply a number with each other, it gets a negative number. And that's where complex numbers come to be. So if you are unfamiliar with complex numbers, I have a video under the Path Background for Physics series. You can check that out. So using the complex numbers, we have the identity that so I can write it here, that the a squared plus b squared can be factorized into a minus I b times a plus I b. So then when we get I times I, that's going to give us a minus sign, and then so when we multiply that minus sign with the other minus sign, we get the plus sign. So using this, we can factorize this Hamiltonian into saying that that's the same as Hamiltonian is the same as 1/2 times m omega squared. That is, those are just numbers, so we can take that out for a bit, and then get that this is x operator minus I m omega for the p, because for the p we didn't have that, so when I factorize it out, then it's going to be in the denominator, and the same thing with the plus sign I m omega of the p operator. So these are the operators that help us define the so-called ladder operators. They are going to be called ladder operators because they help us moving up and down in the energy ladder. The operator that is lowering, so it's moving us down in the energy ladder, is called A. Okay, first of all, ladder operators, and then we have the ladder operator that's moving down, so that's the lowering operator, also called the annihilation operator. Annihilation. So annihilation means that our particle gets destroyed. So the lowering operator, or the annihilation operator, is denoted with A, and it is defined as m omega over 2 to h bar under the square root, and then the same thing as above, so it's x plus I over m omega p. This is an operator, that's an operator, and close this. And we also have the raising operator, or creation operator that would raise the energy or create the energy. And that happens to be actually the dagger of the A, also sometimes just denoted with a plus sign. These anyway look very similar. So that's the one which creates the particles. So the factor before it is going to be exactly the same, 2 omega over 2, oh sorry, m omega over 2h bar, and x operator minus I over m omega of the p operator. So if we put this back here, what we get is that the h operator, is the same as the h omega, h bar, sorry, it's h bar everywhere, h bar omega times a dagger, a, plus 1/2. So that's very interesting that we have this this 1/2 here. It's actually a bit of a surprise, and it's called the 0-point energy. 0-point energy. And you can hear this all around in sci-fi, that they are like harvesting the 0-point energy. In Star Trek, you have the ZPM, which is the 0-point module or something like that. So the whole point of those is that you create like a mini universe, and you just take off the energy from the 0-point energy. So this means that the vacuum has a non-zero energy, right? That's the physical consequence, is that the vacuum has a non-zero energy. That's a big surprise in itself, right? When you have nothing, you would expect that that corresponds to no energy. So actually, the next step that we can do is that we introduce the number operator. So the number operator is denoted as n operator, is actually the multiplication of this a dagger with the a. So that leads to that we can rewrite the Hamiltonian to be h omega n plus 1/2. So what does this n really do? Well, if we have a state with n particles in it, or we have, for now, let's just say that our electron is in the nth state, so particles in the nth energy state, then denote with n. So you should imagine this to be like your electron to be on the 1s2 orbital, and that corresponds to some energy. So when I act on this state with which is in the end energy state on the number operator, then what we get out of that is going to be the n number of that state. So when we act on the state with the operators, the ladder operators, so I just first start with the a. So when we act on the n with the a, then that's going to decrease. That a was the annihilation operator or the lowering operator. That's going to either eliminate a particle or as of now just lower the energy with one state. And there has to be a number here. So that number is going to be the square root of n. And that's because to think about that, if we are in the special case of the vacuum, so the vacuum, as earlier, is the situation when n equals 0. That's the lowest energy state. So when we are in the state 1, and from that we want to move here, then to the 0 state, then we have to somehow make sure that when we try to lower from the 0 state, then there is nothing here. So there is a difference between this is not the same as this. This is the state which denotes vacuum, and this is just the number 0. But then when you do a on this thing, then it would give to -1 state. But because there is this square root of n here, which is going to give us a 0. So that just means that you can't do this anymore, right? Yeah. So that's one of the reasons why we have a factor of square root of n here. And then if we act on a state with the raising operator, so a regular or a plus on the n, will, not that surprisingly, create n plus 1 state here. And the again, with the very same logic, when we apply this raising operator to the vacuum, we should get the state 1. So 0 plus 1 is 1, square root of that is 1. That's how we get to this state. So that means that we get 1 by raising the number of particles in the vacuum. And then that would mean that we get to the state 2 by raising the state of 1, and so on. So if we want to get to the nth energy state, or if we want to create n particles, that we can do by acting on the vacuum with the a raising operator n times. And just thinking about this, we need to make sure that it is properly normalized. So there is a 1 over square root of n factorial in here. And that's actually a very important result, that we build up everything from the vacuum. So everything which happens comes out from the nothing, as they would say. And that's one of the big questions that people are asking sometimes. How could you have something from nothing? Well, there you go. You just use these operators and you get your particles out of it. The next thing to discuss is a bit of a change in the notions. So 3.4 is the so-called occupation number representation. Occupation number representation. So in quantum mechanics, we label each identical particle and we list its momentum usually. So we say that we have the A, B, C state, which is denoted that the first particle has P1 momentum, the second one has P2, and the third one has P3 momentum. So that is the way that we could label a particle like that. So this means that A particle has is in the state p1, so it has momentum p1. A particle in p1 state has momentum p1, and B particle is in the p2 state, has the p2, and C particle is in the p3 state, which then has p3 momentum. In the occupation number representation, however, what we do is that we denote how many particles occupy each momentum state. So if we have two particles which are in the momentum state p1, so two particles are in p1 and one particle is in p2, then if we move to this occupation number representation, that's going to be, A, B, C is going to be the state 2, 1, 0, 0, 0, 0, as many zeros as you want. And so that means that I have, particle A is there twice, but in momentum p1. Particle B is there once. Particle C isn't there anymore. And D and E and F are also not there at all. There is nobody in the third, fourth, whatever momentum state. So we don't really want to write out all of these zeros. So what we will just write here is that this is the 2, 1 state. So there is a special state again, the vacuum. Vacuum is the state when we have 0 in all the states. So that will still just look like this. So again, going back to the idea earlier that we want to build the particles from the vacuum, we can use the same idea as earlier, that we want to have the N1, N2, and so on state. It is going to be that we have the vacuum. On the vacuum, we act with the operator that creates a particle, and that was earlier what we had. And that, so this we did n times. Now what is changing with the occupation number representation is that we create a particle with a given momentum. So I'm going to give an extra p here. That means that I create a particle with momentum p from the vacuum, and so there is an extra p in the index of the n, and we are going to do a product. It's not a sum, but a product for this p, and we should not forget that we had this normalization of n factorial over the square root. That's what we had earlier. So that just changes to np. So again, we are building up particles from vacuum using these creation operators. We could also destroy some, but for now we are just creating a state with the creation operators and annihilation operators, and we create them in slots of different momentums. So that's all for the occupation number representation. The last thing for this video is about the Klein-Gordon equation. So 3.5 is the Klein-Gordon equation, And this jumps back a bit to the Schrödinger equation. So the Schrödinger equation, we said that the energy Schrödinger EQ energy was the same as p squared over 2m plus potential. We made these operators and got the Schrödinger equation. It should be in this direction. And we said that, well, there is some issues with this. For example, that we can only solve it for some special cases, and that it is not relativistic. So what's the change from, what's the big news when we moved to special relativity about the energy? That it was that the energy is calculated using the Einstein formula of E squared equals P squared C squared plus M squared C to the power of 4. So we could move this to the same way that we create the energy operator squared, the P operator squared, C squared plus M squared C to the power of 4. And we can use the same thing that the age or the energy was measured with the energy operator, which is the same as the Hamiltonian operator, is the I, h bar, and the derivation by time. And the P operator was the I, h bar, and the derivation by the space. And we also said that the x operator is just multiplying with x. So if we plug all this in, then what we get is minus h bar squared, then the time derivative of the psi. However, now we have it twice, so this is squared, so we do the time derivation twice, is the same as the h bar squared, c squared, d nabla squared plus m squared c to the power of 4, and this is multiplied with the state. So and now we are happy because there is a c factor in it, and then this is going to be relativistic. As I discussed earlier, that in particle physics, we like to change to the so-called natural units. So natural units, speed of light is 1, and h bar is 1. So if we use that, then what we get is that this equation becomes minus of the derivative by time twice the state, which equals minus d nabla squared plus m squared acting on the psi on the state psi. We can rearrange this a bit and say that we have nabla squared minus the time derivative squared acting on the psi state and gives us minus m squared times the psi state. And if you check out one of the math background in physics videos, then you realize that this is actually what we call the D'Alembert operator and denoted with the box. So box was the D'Alembert operator, also called the box operator. So then this leads to saying that box plus m squared, I edit this to the left side, box plus m squared acting on the psi state is 0. And so actually, when we discussed the D'Alembert operator in the math video, then we also thought about that partial the 4 vector, the d mu. Actually, it was not even in the math video. It was in the 4 vector notion. So d mu times d mu was actually the same as the box operator. So this was d to the second power. This whole thing just means the same thing. So just with this notion, what we get is that d squared plus m squared acting on the state equals 0 is what we call the Klein-Gordon equation, or at least almost. This was actually one of the first tries of Schrödinger, but then he realized that there are some issues with this, so he wasn't very happy. He didn't want to. With this, we kind of end up with having the probabilities of the particle moving with the negative probability. So that was something which Schrödinger didn't like. And that's how he created the Schrödinger equation later. And Klein and Gordon discovered that this thing, although sounds stupid for the states, is actually true for something deeper. It describes the quantum fields, not quantum mechanics, but quantum field theories. So we earlier discussed a bit with field theories, so I'm going to call phi, which is the field corresponding to the x mu location, is a field, a quantum field, or as of now, just a field. And so Schrödinger didn't like that, moved on to the Schrödinger equation, but then Klein and Gordon, around the same time, said that, well, this stuff seems to be true for fields. And so the D'Alembert operator plus the mass squared acting on the field phi at the x mu location equals 0 is true. The last thing for this video, let's put together the last two things that we learned now. So 3.6 is going to be field creation and annihilation operators. So field creation and annihilation operators. So since we just discussed a bit about the creation and annihilation operators in quantum mechanics, and we had our first glance at quantum field theories with the Klein-Gordon equation, it's a good time to go a bit into this generalization of the ladder operators. So we said that the A, B plus operator or dagger, doesn't really matter, depends on whose book you're reading, is the one that creates a particle with p momentum. So actually there is one more complication which you can do, that this p is a vector, so I could have the underlining there. And so the A, P, let's just call it a vector this time, is the one which destroys a particle with p momentum. So because we create them with a fixed momentum, which can also be said that they are localized in the momentum space. It really just means that we created them with a fixed momentum. We didn't create them at a fixed point. We created them with a fixed momentum. And because of the Heisenberg principle, the uncertainty principle that we discussed earlier, we mean that if we have a localized quantity in the momentum space, they will be not localized in the position space. So we didn't really go too much into the formula that describes that how much we don't know one of the quantities means that we know has to know the other quantities. So this is one of the exercises in the book. So I don't really want to go too much into the details, but from the Heisenberg principle, we know that the delta x, delta p is a number. So if this is a small number, if this is small, then this has to be big, or the other way around, because it has to be one constant number here. So based on this, that means that these p states are localized in momentum space, and all that we discuss means that they are not localized. They are delocalized in the position space. In order to express them in the position space, so now if you want to move from the P, well, not an operator, just the P space, to move from the P space to the X space, we need to do something which is called a Fourier transformation. So when we want to have a field creation operator that creates a particle at the position x, that's going to be denoted psi. Psi dagger was the one which created something, it's an operator, and it creates the particle at x, so that's important. Now we have an x in the body of the operator. What we will do is that we will have the operator that created something at the p position, and we will apply the Fourier transformation on it. So the Fourier transformation is what I have with the blue. It is going to be that we multiply this with the exponential of minus I p x. These are vectors, and we sum for all of these p vectors. What is in blue is the Fourier transformation, and then there is also a factor of n for the normalization. N is for normalization. And we can do the same thing with psi operator x. This is going to be the annihilation operator. We do the same thing. We have an AP operator. There is no dagger, so it is destroying particles. We have the add IPX. And what's different now is that we change the minus sign into a plus sign. But we still have the summation for P, and we have our normalization factor as well. So with this, we reach a very important point in the quantum field theories, as I mentioned earlier, that this means that we can build particles from nothing, from the vacuum. We can just destroy them, build them again, and so on. So it's a really messy thing where you create and destroy and create and destroy and destroy and destroy and create particles as you wish. This was something, by the way, which quantum mechanics couldn't do, but quantum field theory can. So quantum mechanics could not create slash destroy particles. But quantum field theory does it all the time. It's essentially the definition of a quantum field is that it's built up from creating particles from nothing. Okay, with this we reach the end of this video. We really have understood that the Schrödinger equation is just the direct consequence of time evolution. And to include special relativity into the picture, we need to upgrade our theory into quantum fields. We discussed that the uncertainty principle comes from the fact that certain operators cannot commute with each other, and we by this we reach the Heisenberg equation. There is a version of the Heisenberg equation that is more widely known. However, we didn't derive that in the class just because it is one of the exercises in the end of the chapter. We also realized that these quantum field theories allow us to create and destroy particles out of the vacuum. And we reached the point of understanding that these fields themselves are actually a special sum of these creation operators. With all this, finally, in the next video, we can build our first quantum field theory. And in the beginning, we will just start with the simplest case, but in the end, we will end up to describe massive scalar particles. As always, please like this video, ask questions in the comment section, and subscribe so that you get a notification about when I upload my next video. Thanks.